All right, so last time we were talking about wavelength and frequency and how there was this whole electromagnetic spectrum here of light. And wavelength and frequency were two of the properties that we could talk about for light. There's actually a third one, and that is the fact that light also carries energy. And this is where the particle part of light comes in. We've been talking about waves, light as a wave, but I told you that light also behaves as a particle. And so the particle part is where the energy part is going to come in. So you'll see this one is in order from longer wavelengths to shorter wavelengths, or it's also from lowest energy to highest energy. And you'll notice here, you can see in this particular chart, you see frequency, you see energy, and then you see wavelengths. So we haven't talked about energy yet, and that's what we're going to get into in our next section. So the electromagnetic spectrum, again, remember they're inversely proportional. Wavelength, if the wavelength gets bigger, the frequency is smaller. If the wavelength is shorter, the frequency is higher, which makes sense, right? More waves are going to pass per second. You're going to get more full waves per second if the wavelengths are smaller. The visible spectrum, this is just the light that we can see. Notice here how it's measured in nanometers. And the reason why is because the wavelength is so small for visible light, it doesn't really make sense to measure it in meters. It's going to give you these really tiny numbers. And so because nanometers gives us kind of normal numbers, usually wavelengths are measured in nanometers for visible light specifically, which you hear a lot about visible light in biology. Like we talk about photosynthesis using particular wavelengths of visible light. So this is just sort of showing here. As the wavelength goes up, the frequency goes down, and vice versa. This is just another one showing all of them, the electromagnetic spectrum here. Now, one way you can memorize the colors in increasing energy, and we haven't talked about energy, but energy and frequency are actually directly related. So the higher frequency light would also be a higher energy light. You may have learned Roy G. Biv. This is like a cute little way of memorizing like the colors of a rainbow in order. So it's red, orange, yellow, green, blue, indigo, violet. So now that is in order of increasing energy, which means it's going to be in order of shorter wavelength. So red would actually have the longest wavelength. It actually has the least energy. And violet has the most. This is our shortest wavelength, our highest frequency, highest energy. One thing I think might be helpful for trying to remember what the correct order is, if you're thinking about energy, think about how UV light is dangerous to you, right? UV light is the one that actually leads to skin cancer. So UV, ultraviolet, comes right after violet. So think about if UV has the highest frequency and it also happens to have the highest energy, that is going to that's going to be on this end of the spectrum. It's going to be the one with the shortest wavelength. And red over here is infrared. And again, that has less energy, longer wavelength than red. So that might be one way to remember if you're trying to remember, well, which one, the red or the violet is the one with the highest energy, the highest frequency as well. It's going to be the violet. All right, so like I mentioned, a lot of times these different wavelengths of light are not measured in meters because meters are so tiny. So I wanted to remind you, I went through this on a previous slide, but I want to remind you one more time, if you need to do a conversion, so we typically will provide you with the conversion factors. You don't have to memorize what a nanometer is, but you do need to know how to convert. And I also saw some problems you'll have to do where you also have to convert like megahertz to hertz or kilohertz to hertz for frequency. So just a reminder, if we want to convert, our sig figs won't change. So 450 with a decimal that has 3 sig figs, our answer will still have 3 sig figs. Here's how you could do your conversion. You write the original number, 450 nanometers, times, and then we're going to turn this into a conversion factor. Now, you can actually use either of these. They're the same. 1 nanometer is 1 times 10 to the 9th of a meter, or 1 meter is 10 to the 9th nanometers. These actually will work the same way. So I'm going to actually use this one. So 1 nanometer is 1 times 10 to the negative 9th meters. So what I'm going to do is I'm going to turn this into a fraction. I want to put nanometers on the bottom. Why am I putting nanometers on the bottom? Because that way it will cancel. I always want to put the unit I'm converting to on the top. So nano will cancel, and my answer will be in meters. And then this is going to be 1 times 10 to the negative 9th, and now I just have to multiply. Now you'll get the same answer if you do it this way. 450 nanometers times 1 meter is 1 times 10 to the 9th nanometers. So this would be, in this case, you'd end up dividing by 1 times 10 to the 9th, which happens to be the exact same thing as multiplying by 1 times 10 to the negative 9th. So no matter which way you set this up, nanometers is going to cancel, and then your answer here is going to be 4.50 times 10 to the negative 7th meters. Now, remember, if your calculator doesn't give that to you, some of your calculators may actually give you like 1, 2, 3, 4, 5, 6, 4, 5, and they're going to drop the 0. Your calculator doesn't know how many sig figs are in your number. So be very careful because it's probably not going to give you 4.50. It's probably going to give you 4.5. So you've got to remember from our numbers chapter, 3 sig figs, we keep 3 sig figs. If your calculator does give you this, some of them do have a button, SCI button, and you can change it to scientific notation, or you can put it into scientific notation yourself. You really shouldn't be giving me this number. That's a ridiculous way to write a number. All right, so that's just a reminder. So let's move on. So Planck's theory. So Max Planck, he said that objects absorb or emit energy in tiny pieces called quanta. The singular of this is quantum. Now, what does that mean? What it means is that energy is not like, a lot of times we think of energy as like a ramp. Like you think of a dimmer switch in your living room and how you, or your kitchen, dining room, bathroom, how you turn the light up or turn the light down by making it more or less dim. So it may seem like when you're doing that, that it's like a spectrum without any gaps. That I can make it, I can stop it anywhere I want to, like a ramp. You can, if you're walking up a ramp, you can stop anywhere you want. What Planck said was that's not exactly how energy works. It's not continuous like a ramp where I can stop wherever I want. It's more like stair steps. So think of the packets of energy as stair steps. So I can't step in between stairs. I can either be on this step or this step. And he's saying that this amount of energy is a quantum. Now you might say, well then why don't I notice that? If I turn the lights up or turn the lights down, I don't notice it stopping at discrete points. It looks like it's continuous. Because a quantum is such a tiny, tiny, tiny amount of energy that you're not going to notice the change. To your naked eye, it seems like it's just a ramp. But in reality, it's stair steps. Imagine going up a ramp, but the ramp actually is made like this. You're not going to notice that. To you, it's a ramp. But in real life, if you were an ant, that would not be a ramp. There'd be steps. So think of it that way. All right, so this was sort of discovered along the line, kind of from some experiments, but one of those is something called the photoelectric effect. This was, what they discovered was when you hit metals with different frequencies of light, sometimes nothing happens, and sometimes electrons shoot off the metal. And so Einstein explained this by saying that light consisted of quanta of energy called photons. And a photon contains a particular amount of energy. It contains a particular number of quanta, and it gives that photon a particular amount of energy. And if the light had enough energy, it excited the metal. And if it didn't, then the metal did not get excited. And I'll show you some examples of this in class. But infrared shoots a beam across if you have a garage door opener. And the reason why there's usually like a safety there, that if you break that beam, the garage door won't close on you. This receiver only is affected by infrared. I could shine a different light in there and it's not going to trip this. It's got to be that specific wavelength. And this is showing another picture of the photoelectric effect. And I'm going to show you some examples in class. I have some beads that are only, they light up in different colors. Maybe you've had a t-shirt that does that. And it's only affected by UV. So you go out in the sun and like your t-shirt changes colors and lights up. But if you shine, doesn't matter how hot the light is, how bright the light is in your house, shining a light bulb on that t-shirt doesn't do anything. And so this is what it's showing when light hits a metal, shines on a metal. It either is below the threshold and nothing happens, or it's above that threshold and you actually see electrons actually repelled from here. And so this is called the photoelectric effect. So there's some math that goes with this too. Remember I told you that we were going to talk about how light also has energy. And this goes more along the lines with the particle idea of light. versus the wavelengths of light, because light has what we call a dual nature. And so this is the formula, that energy is equal to H times frequency. So this V, remember, is that Greek letter, nu, it's frequency, and H is Planck's constant. 6.626, sometimes you'll see this as 6.63, sometimes they'll round it, times 10 to the negative 34th, and this is joule seconds. That is the units for this, joule seconds. Energy is measured, our standard metric unit for it is joules. Another measure of energy is calories, but we don't usually use that. That's not our metric unit for it. Joules is our metric unit, but I'm sure you're familiar with calories. So the formula for one quantum or packet of energy. So this is again just showing the photoelectric effect. So this happens to be potassium. If you hit it with red light, nothing happens. But if you hit it with green light, it actually does shoot off electrons. If you hit it with, I don't know if this is supposed to be violet, it also shoots off electrons. So red does not have enough energy. The packets of energy in red, the photons of red, don't have enough energy per photon to cause this effect to happen. All right, again, if I just make the light brighter, that's increasing the amplitude. That's not going to cause anything to happen. And again, I'll show you this in class. I have these, like a colored filter, and I have some sensitive paper underneath. And you'll see I'll shine a white light on that, and you'll see that I'm going to filter it out by color, and only certain colors will actually cause that paper underneath to light up. So red light hitting sodium has no effect. Violet will cause electrons to be expelled. You don't have to memorize that. It's just giving some examples. Again, glow-in-the-dark things that are only stimulated by UV light would be an example. I can show a regular light on there. It could be a hot light. It could be a bright light. If there's no UV in it, it's not enough to stimulate it because you need that minimum energy of UV to cause the stimulation. Okay, so you can get problems with this same formula. What is the energy of a photon? All right, so let's take a look at this one. So here's our formula. Energy is equal to Planck's constant times the frequency. Now remember that the frequency here, H, is 6.626 times 10 to the negative 34th joule seconds. Now, again, this is why I stress to you that you should write your units, because then you'll know what's going to cancel and you'll know you're doing it right. So our energy is going to be equal to H 6.626 times 10 to the negative 34th joule seconds times 2.22 times 10 to the 14th seconds to the negative 1. Now look what's going to happen here. Seconds to the negative 1 and seconds will cancel, because seconds to the negative 1 is basically 1 over a second. And now our answer would be given in joules. If you want to try the second one, here is your answer. Remember, manipulate the formula first. And remember, our sig figs will always be based on our original measurement, not on Planck's constant.